Okay, so let's take a look at this gutter problem, and this should be similar to a problem there in 4.4. I think, let's see, I think it's going to be similar to problem number 15 in 4.4. All right, so here's what's happening. You know, usually if you've ever seen them make gutters for a house, they usually come in with a roll of flat metal, and then they bend it on site. And that's what's happening here. We have some flat metal that is 20 inches wide, and we're going to go ahead and bend this up into a gutter. And so the gutter is going to be three-sided, and it'll be meeting at 90-degree angles here. So we're going to go ahead and take a look at the questions. It says, what depth would provide maximum cross-sectional area and hence allow most water to flow? Cross-sectional area would be as if we looked at a slice of this drain pipe. How much water would represent the rectangular area right here, which is really just length times width, right? So if we went and did this, we would go ahead and take a look here and say that, well, if we were looking at length times width and we're after a depth that would provide the maximum cross-sectional area, we need a function so that we could go ahead and find what would really be a vertex value, right, a maximum value. So in order to write this function, I think we could say this, that the area or the cross-sectional area is really a function of the depth, right, of x. And that function comes from length times width, which, here's what they did. They figured if this was 20 inches wide originally, and you bent up X amount on each side, which we're going to calculate, the remaining amount that's left for the bottom of the drain of the gutter is going to be the original 20 inches minus an X and another X, or minus 2X. So we have an X by 20 minus 2X situation, which we could just multiply together. That's X times 20 minus 2X. And that gives me, I'm going to go ahead and reverse the multiplication so I get an AX squared plus BX order here. So I'm going to go X times negative 2X is negative 2X squared, and X times 20 is 20X. Oops, got the square there. Okay, so there's our function, right? So now let's answer that question. Let's answer the first one. And it was, what depth will provide the maximum cross-sectional area? Well, that would be, since depth is x right here, that's our input value, that's a domain value, right? We could go ahead and find negative, it's going to be the x-coordinate of the vertex, or negative b over 2a. And so the x that provides maximum area is going to equal negative b over 2a, which would be 2 times negative 2. And that answer is going to be negative 20 over negative 4, or a 5-inch depth would go ahead and give us the maximum, right? And it would turn out, by the way, if you made this 5 and this 5, then this would leave 10 for the bottom here, so it would be 5 by 10, right? Okay, so that would be the answer to A, and that's 5 inches right here. Okay, so there's a second question. It says, what depths will allow at least 42 square inches of water to flow? At least 42 inches of water to flow. By the way, we noticed that at 5-inch depth, we have 5 by 10, or 50 square inches of water. That would be the maximum. So if we were here on a little graph that I drew and comparing area to depth, we'd have this 1, 2, 3, 4 at 5 inches of depth. We ended up with this area up here of 50 square inches of cross-sectional area. But imagine that we had this kind of thing. Now obviously if we had no depth at all, it would be the flat sheet of metal and there wouldn't be any cross-sectional area. So we have this kind of quadratic kind of thing going on here, right? We got something like this. So what we want to know is at 42 square inches of cross-sectional area, what would be, and there'd actually be two answers, right? What would be the depth that would produce 42 square inches of area? We want this point and this point. Well, how are we going to do that? Well, since that's an output, I think we should set our function equal to 42 and solve that. So we'd have 42 is equal to, so that's a of x. So we have 42 is equal to negative 2x squared plus 20x, and we're going to solve this, right? Well, I don't prefer to solve quadratics where, especially if I might try factoring on this, who knows, it might just factor. So I think I'm going to go ahead and move these terms to the left. We're setting the equation equal to 0 for the purpose of either factoring or, if we have to, the quadratic formula. And now, since 2 is a common factor, and I might try factoring, it would be a lot easier if I just would divide both sides by 2, just to get my numbers a little smaller, to give me a better shot at trying to factor. And I have this. And by the way, that's just a page number. I'm on the second page of this handout. But what we got here is a situation where this does factor, because the two numbers that multiply to 21 and add to negative 10 happen to be negative 3 and negative 7. So what I have now is, according to the zero product property, two answers. X could have been 3 or X could have been 7 inches of depth. And so what we're saying is, at both 3 and at 7, we'd end up here at 42 inches, right? It would be kind of like this. And also over here at 7, right? And so they would be the two different drain pipe combinations or gutter combinations. In other words, if we had a 3-inch depth, that pipe would be, or that gutter would be 3 and 3, that would be 6. And 20 minus 6 would be, it'd be a 3 by 14, and that would give you 42 square inches right here. Well, what would the other one be? That would be a 7 and 7, and that's 14, and if you take 14 away from 20, you'd have a 7 by 6 would also be 42 square inches of cross-sectional area. So they would be our two solutions.